Okay, welcome everybody to the GA Wednesday seminar. This morning we are lucky to have Phil Cummins talking to us about tsunamis and earthquakes. Phil really doesn't need any significant introduction from me. He is, I think, the leading scientist in our community safety area of activity, or the value stream if you like, and he holds a position that's jointly between GA and ANU, where he holds a chair in natural hazards. What this means is that we get access to the latest research that Phil and others at ANU undertake to feed into our community safety program, and through the community safety program, of course, both through that program itself and through Phil's efforts as well, it gets disseminated as soon as it's practicable into the region. So Phil is a shining light of research being applied to Australia's most important challenges, if you like, as our leitmotif is. So I've known Phil ever since I've been here. We were both on the inaugural Geo Plus cohort in 2004. Without further ado, let's pass over to Phil, who's going to talk to us about new approaches to tsunami and earthquake source characterisation. So Phil.
Thanks very much, Andy, and I wanted to thank Jane and Adrian for inviting me to give a seminar. I think Jane told me something to the effect that it's time for me to put my big boy pants on and give a seminar. So here I am. I want to point out that this is, I noticed there are some people from RCS in the audience. It is the seminar. It's very similar to the seminar I gave a couple of months ago, so I hope you guys have not seen it before, but I apologize if you have. Also, Jane wanted me to be very careful about not going into too much technical detail. And there is, I have to apologize to the rest of you, there is a bit of technical detail in this talk, but I'll try to just sort of explain it in a way that that will be, that you'll be able to follow it. And I'll gloss over it, but give you enough explanation that hopefully you get a flavor of what's going on. This talk, well, let me just go over so I'm going to discuss new approaches to tsunami and earthquake source characterization. This is a number of my students and postdocs at RCS have been working on this from a couple of different angles, and I'm going to try to present most of that work in a way that's somewhat coherent. It's going to be about megathrust earthquakes, and I wanted to talk a little bit about them in general. Who cares about megathrust earthquakes? These are the biggest earthquakes that the world experiences. They happen in the Earth's subduction zones where two plates are coming together. I'll get into more detail about that later. But I did want to show this figure from a talk by from a paper by Thornley, in which he pointed out that the world has experienced quite a few of these in the past few years. They do tend to occur in clusters. The megathrust ones are these in Kurils, Japan, and in South America, and then these along the Sumatra subduction zone. There are a few others here that have been some large subduction zone earthquakes, but we'll be talking mainly about the thrust earthquakes that have occurred in Indonesia, Southwest Pacific, Japan, and South America quite recently. They do seem to happen in clusters. So you can see this is a magnitude on this axis, and then time from 1900 to 2010 on this axis. And you can see that there was a cluster of large events that occurred around the 1960s. That was the big 1960 Chilean earthquake and 64 Alaska earthquake. And now recently we seem to be entering another phase in which we're seeing a cluster of these really large earthquakes. These earthquakes really are massive. This is also from Thorne's paper, in which he shows the moment, the seismic moment, which is, as you may know, magnitude is a logarithmic measure of earthquake size. So you just go, as an earthquake increases by a factor of 10 in size, the magnitude unit goes up 1. But if you actually measure the size in moment, you realize that a magnitude 9 earthquake is much bigger than a magnitude 8 earthquake. And this shows the cumulative seismic moment from all the earthquakes in the world. And you can see these very large steps. This is all the earthquakes in the world. And there are these large steps in this, which are associated with just these single earthquakes. The Chilean earthquakes, you can see that it was responsible for quite a large fraction of the total seismic moment budget in the Earth during the 20th century, and similarly for the Sumatra and other recent very large megathrust earthquakes. It's important to point out that although these are very, very large, they're not necessarily all that deadly. And in fact, much smaller earthquakes can be much more deadly. This is a list on the left. This is a list of some of the largest earthquakes in the world. You see 1960 Chile at the top, a magnitude 9.5. Killed almost 2,000 people. Of course, the Sumatra earthquake killed many more. Some of these earthquakes killed a lot of people, some didn't kill any. In 1952, Kamchatka, magnitude 9, 0 deaths. The ones that did kill a lot of people generally did it because they generated large tsunamis, usually large local tsunamis. That can kill a lot of people. But, you know, if it's in an area where there aren't that many people and the energy is directed toward coastlines that aren't that populated, even a very large earthquake might not kill that many people. And it's worth pointing out that, on the other hand, much smaller earthquakes can kill many more people. The Haiti earthquake 2010 killed more people than the 2004 Sumatra earthquake, even though it's over 100 times smaller. That's because it's a much smaller earthquake. It occurred right in a city, and it occurred in a city that where the construction standards were very poor, and we've seen that very recently in Nepal. So these much smaller earthquakes can actually kill a lot more people because they can occur right in a city, whereas the subduction zone earthquakes are occurring offshore. So you know, in some cases they actually don't kill that many people. But on the other hand, when they generate large tsunamis, and they generate large tsunamis adjacent to a populated coastline, they can kill a lot of people, and it can be very damaging. So just recently, 2004, we had the most deadly tsunami disaster, almost 250,000 fatalities, and then the 2011 Tohoku earthquake was the most expensive tsunami disaster in history, $235 billion in economic loss. So they can be very damaging and very deadly. But they don't always have to be, and other earthquakes, other much smaller earthquakes can be equally deadly. I just wanted to go over a few basic sort of facts about megathrust earthquakes. One, there are weak faults. Giant earthquakes occur due to the very large rupture area, not due to high stress or high strength of the fault. And the tsunami excitation, the bulk of it seems to be caused by elastic deformation of the seafloor due to slip on the fault. This is the classic, elastic rebound hypothesis, and when that happens on the seafloor, it moves the water. It moves the water out of equilibrium. And you know, I'll get into both of these in all three of these in a bit more detail. Yeah, this elastic rebound is due to stress accumulated by relative motion across the plate boundaries. So I'll just go over those very quickly. How do we know that megathrusts are weak faults? Why do we say that? Well, you know, these happen when two plates are coming together and one plate is diving beneath the other. Let me get this arrow here. One plate is diving beneath the other. This is sort of the ocean plate here diving beneath either Sumatra or Japan or whatever subduction zone you're dealing with. And if there's any reasonable amount of friction on that boundary, if that boundary is strong and has a lot of friction, it will generate a lot of heat. And we really don't see that. We do see this is the heat as you go from offshore to onshore. This is actually from the Pacific Northwest, some modeling done by Kaylin Wong. And you do see a fair bit of heat, but it's not what you really expect for a high frictional contact. And so, in fact, if you try to model the frictional coefficient of these contacts, you get very low 0.03, 0.05 friction coefficients. So if we look at the heat generated in a subduction zone, it seems to suggest that the friction is very, very low. Furthermore, if you look at the stress that's generated inboard of these subduction zones, it's not always compressive. You would think that if these plates are coming together and there's a lot of friction, a lot of strength on that contact, that it would put the upper plate into compression. And that doesn't always happen. So, for example, in southwest Japan, if you see a lot of sort of crosses there, it means that there's compression. In southwest Japan, you don't see compression. In fact, in southwest Japan and places like Cascadia, the faulting regime is strike-slip. It's not a thrust regime. So you don't actually get that much compression. And the only way that can happen, because we know the contact that has friction and generates earthquakes is quite wide in southwest Japan, it must be very low, because you'd sort of add up all these forces acting all over this wide seismogenic zone, should be building up stress in here, and because it doesn't, we know that friction must be pretty low. It really doesn't build up enough stress. On the other hand, this was a paper also by Kaylin Wong in 1999, and they pointed out that in northeast Japan, this was 1999, that it was compressive. And the only way they could get that, if it was a low frictional boundary, was if the seismogenic zone was very, very wide. And that would imply that you could get very large earthquakes in northeast Japan. And this was done in 1999, and in fact it wasn't until 2011 that we finally realized that in fact you can get very large earthquakes in northeast Japan. So in any case, all of this is consistent with very low frictional coefficients. You can see the friction coefficient here, 0.03 and 0.03, very low. So it's a weak boundary. That's also consistent with the fact that the stress drops are quite low for megathrust earthquakes. And then I wanted to talk a little bit about that most of the tsunami generation is due to elastic rebound due to strain accumulation. There are other hypotheses for the tsunami generation in a large earthquake. One, for example, is slumping and landslides. I'll try to talk a little bit more about that later. But a lot of after the Sumatra event as well as the Tohoku event, people go out and look for evidence of massive landslides because they just can't believe that this huge tsunami was generated only by an earthquake. And I think the evidence, and there are also people who look at some of the faulting in the accretionary wedge that's sitting above the subduction zone, and they say that there's lots of sort of faulting that might generate block movement here. These guys are talking about the potential for this block to have sort of been forced out due to the fault motion in the accretionary prism, and that also could displace a lot of water. But these mechanisms, in my opinion, really, they might contribute to the tsunami generation, but by and large, most of the tsunami generation is caused by the elastic rebound due to the strain accumulation on the fault. And you know, we have a lot of, in this earthquake, we have a remarkable number of observations. In the 2011 Northeast Japan earthquake, we have a remarkable number of seafloor observations. These have been used these include ocean bottom pressure gauges. In Japan, they have cabled and buoyed ocean bottom pressure gauges that measure the pressure on the sea floor, and they can detect uplift, they can detect movement of the sea floor. They also do this sea floor GPS. They've been doing this over the past couple of decades, where they actually have some sensors or some transponders on the sea floor that send a signal to a ship, which is then precisely located using GPS. It's a very, very impressive, very, very impressive technology that, you know, they've built up very slowly over the past few decades, and they're now able to do very precise measurements of seafloor motion. This is very impressive because you can imagine, anyone who's been out on a ship can imagine that, you know, this ship's moving around, and to measure to centimeters the motion of the sea floor, which is, you know, it could be 3 kilometers below the ship. It's a very difficult thing to do. And the Japanese have now been doing it. They can get accuracies of several centimeters on the displacement. And you can see this is the kind of thing they saw prior to the 2011 Japan earthquake. There was basically no movement, and then suddenly, boom, there was this large co-seismic offset when suddenly the fault moved and the seafloor moved up, and in some places it moved down. But the point of that is that all of these measurements seem to be consistent with elastic rebound. If you got a landslide or some kind of fault movement, they would produce signals like this that were not compatible with elastic rebound, but you know, virtually all, with some exceptions, virtually all the data suggests you can use elastic rebound to explain the tsunami generation. And I'll illustrate how that happens in this slide here. Let's see, I've got to do this, got to get the mouse there. This was a really nice animation generated by Tony Pack's team at GA, in which he shows the Eurasian plate here, the Australian plate subducting beneath Eurasia. This is intended to be Sumatra, and you can see stress is building up, and this plate is being compressed by the friction along the plate boundary. Stress builds up till it exceeds the frictional strength, and then the plate pops up, displaces water, and that travels outward as a tsunami. So that is how a tsunami gets generated by a megathrust earthquake. And this is what I mean when I'm talking about elastic rebound. It is this I'll do that one more time. It's this accumulation of elastic strain. You can see this plate being compressed here as this thing starts to move. There's friction on this contact. This plate's being compressed. It's building up elastic strain. The stress on the boundary is building up, and finally it will break. And this is all just elastic deformation. It's very easy to model, actually, and that's how the tsunami gets generated. And you can see also in that there was movement on the sea floor all during that time, both prior to the earthquake and at the time of the earthquake, and that's what's measured. We can now directly measure that, at least off northeast Japan, using seafloor GPS as well as ocean bottom pressure gauges. So we measure these things. We measure the seafloor movement. We measure the movement on land using GPS. We see seismic waves and we see tsunami waves, and we can use all of these. We can, if we know the generation mechanism, which I've argued that we do, we can then model the generation of the tsunami and the seismic waves and the movement of the ground, and we can invert those measurements to get a model of what happened on the fault. And you probably have seen these kinds of models before in some of the web pages coming out after the 2011 earthquake. After the 2011 earthquake, within a month, there must have been dozens of these models. And these models are showing how much slip occurred on the fault. This is northeast Japan here, over here, and you can see this is the subduction zone here. The Pacific Plate is subducting beneath Japan, and all along the fault, the fault, the upper plate slipped up, and you can see this red shows where there was very high slip, where there was a lot of plate movement, and you can see that there was very high movement right near the trench, which is very efficient for tsunami excitation. And you can see that it extended pretty far down dip, over 100 kilometers down dip. And all of these models seem to be in pretty good agreement. They show that there was maximum slip right at this point. I very carefully tried to align all these figures so you can see the maximum slip happens at pretty much the same point. So, to some extent, they're all in agreement. They all assume the same models, the same model for tsunami generation, but they all use different data, and they're all in pretty good agreement until you start looking at some of the details of this. And you can see, for example, the tsunami model. I should explain, this was the model derived using geodetic data, so this was using ground movement, precise movements, precise measurements of the ground movement in the earthquake. This was derived using tsunami data, so the generation of the tsunami was modeled and then inverted to get a model for the fault slip. And this was using seismic data. So similarly, the seismic waves were modeled from the fault slip and then inverted to estimate exactly what the spatial distribution of slip was. And you can see that they all agree pretty well, except for some of these details, like the tsunami model shows quite a bit of slip to the north. And you don't see that in the geodetic or the seismic models. Also, if you look carefully at the maximum slip, the tsunami model has about 40 meters maximum slip. The seismic model has about 63, and the geodetic model has about 70 or so. So those are all very high numbers actually, surprisingly high. But they are in some disagreement. I mean, you're going from about 40 to 63. That's a substantial. That's about 50% error. And so you might wonder, is that significant? Do we? Well, certainly I would say that we care about that, and I'll get into that in a minute. But, the question is that significant? And I would argue that it is very important, first of all, to know that number, to know what the amount of slip was and where it occurred, because if you can get that much slip near the trench axis, it leads to a lot more, very much more efficient generation of tsunamis than if you had that slip either down dip or a much smaller magnitude of slip. Why didn't it rupture that way in previous earthquakes? Previous earthquakes, I didn't really get into that, but in northeast Japan, we've never seen that in any earthquake, that you get these massive, tens of meters of slip right near the trench. I would argue that we never seen that before in a large megathrust earthquake. If a rupture area as large as, say, 1960 Chile, which was, the largest earthquake in the world, if that whole fault could have slipped by 70 meters, you would have got a maximum magnitude of 10 for that earthquake, much larger than, any earthquake ever recorded. So, we don't really understand, if maximum slip can go up to 70 meters in one spot, why can't it go up to why can't it be that high in other spots? And therefore, why can't it be that way all along the fault plane? You could get earthquakes of magnitude 10 if that were true. So we really have to understand why that happened, and why that happened, and why does it only happen in isolated spots. The other reason it's really important is that recurrence intervals are generally longer than the historical record. That's very common. That's why we didn't know No one knew that the Sumatra earthquake would happen because we didn't have historical experience of that particular earthquake. The previous earthquake, which is thought to have occurred in the 1300s, wasn't available in the historical record. We didn't know that that happened. And the way that you try to estimate recurrence times is by taking what you think the maximum slip should be and dividing by the convergence rate. So, and this is quite important. So in a place like Tonga, for example, Tonga is the fastest converging trench in the world. It converges at 20 centimeters per year. So if you had only, so you should get you should get a very short recurrence time, and if large earthquakes occurred on the Tonga Trench, we should have seen it in the historical record. At least people have argued that in the past. But if slip can get up to 70 meters before you get an earthquake, even the Tonga Trench could experience very large earthquakes. So if slip can go up to 70 meters, what that means is that recurrence times could be even longer than we thought. So we think that they can be hundreds or even 1,000 years. They could be even longer if we have to wait till the slip deficit accumulates to 70 meters before an earthquake happens. So that's another reason why it's important. And finally, we really need to, if we want to understand the physics, we really have to explain this. I mean, there have been a number of hypotheses for this, that maybe there's some kind of velocity, there's some kind of strong material up here that, previous earthquakes, they couldn't break that, and then finally, for some reason, this earthquake managed to break through this sort of strong material at the trench axis. But, we really just don't understand. Another hypothesis is that it was a dynamic thing called dynamic overshoot, where the large slip down dip, forced this stuff up even farther than the strain accumulation would have suggested it could move. We just don't understand the physics behind this, about how the slip could have been that big. But it is odd. I don't think I mentioned this later. The material, I mean, they've drilled down, actually. It was another remarkable thing that the Japanese did. They actually did they quickly, sent the Chikyu out there and drilled down to the seismogenic zone, and it's clay. The clay somehow can accumulate enough strain that it can slip 70 meters. It weighted and accumulated strain. It must have accumulated a lot of strain in order to slip 70 meters. And previous to this earthquake, I wouldn't have thought clay could do that. Clay is soft. It shouldn't be able to do that. So there are a lot of things a lot of questions that this brings up. How can we get slip that's that big? And we have to ask, of course, is it really that big? And are our measurements, our estimates of that slip, how significant are they? How accurate are they? As I've mentioned, there have been many fault models that came out from this earthquake. I better watch the time here. Yeah, I better get moving. I'm going to run out of time. So I better start moving. So anyway, there were a lot of slip models that came out after this earthquake. These are a couple of the first ones that came out. This was done by Simons et al. Using tsunami geodetic data. This was done by Ammon et al. Using seismic data. And you can see that these have maximum slip down dip. They don't have maximum slip right at the trench. And somewhat after the earthquake happened, it was maybe a month or two afterwards, these guys at Jamstec they had done a very precise bathymetry measurement right in that area. And they went out and they did a repeat measurement. And they found that, I don't remember exactly how this goes. This is the difference between the before and after measurements. And they found that they could detect a very large movement of the trench to seaward. So this was the first direct measurement of seafloor movement, and it indicated that there had been essentially over 50 meters slip on the fault. So that this is the trench, and this is where they did their survey, their repeat survey, and they took the difference in that. They found that the trench, the actual bathymetry, they get a shape of the bathymetry, and it actually moved 50 meters, and they were able to detect this and measure this directly. So that was the first indication that there had been a huge amount of slip. And after that happened, then lo and behold, all the models had very high slip near the trench. And so the generous interpretation would be that once these guys had got all the data and analyzed it more carefully, they came up with models that agreed with the bathymetric measurement. A less generous interpretation would be that once they heard that there was this clear indication that there was this massive slip, they sort of tweaked their inversion algorithms, and sure enough, they were able to come up with something that validated that. So, who's right? We don't know. And is that a significant difference? Is the difference between this model and this model significant? We really can't say, because the inversion algorithms just aren't good enough. This is some of the technical detail I'll gloss over, but it's a really simple the inversions that they use for these finite fault models are really simple. They're just least squares inversions, and there are many assumptions that go into them, many tuning parameters, and the bottom line is that you really don't know how significant they are. You really can't estimate uncertainties for almost all of these models. So we don't know. We can't look at one model and say it's significantly different from another model. So to try to address some of these issues, we tried to take some new approaches to finite fault inversion. This is an approach done by my student Roberto Benavente at RCS. He's using what's called the W phase. I'll try. I'm going to have to move a bit faster. So the W phase is this really long period energy. This is the seismogram, and in fact, I think this is the Sumatra earthquake. I've actually forgotten. I've used this so many times. I think this is, let's just say, it doesn't really matter. This is the Sumatra earthquake. The first driving wave is the P wave, and then you get the S wave, the shear wave, surface waves. This is a typical seismogram from a large earthquake. But if it's a really large earthquake and it's a good broadband record, good, very high quality instrument, you'll see that there's this sort of long period ramp between the P and the S wave. And this has been called the W phase by famous seismologist Hiro Kanamori. And he's shown that this can be used. It has a number of very useful properties that can be taken advantage of to understand the earthquake source. I guess I won't go into all of these, but although it looks like a very subtle feature on the seismogram, it's very stable. And so you can use this to get a lot of information actually about the earthquake source. And we were wondering, so he applied that to point source estimates of the earthquake, getting the magnitude of the earthquake and looking at the moment tensor of the earthquake. We wanted to see if this had enough information to actually understand the distribution of slip over the fault plane. And this is surprising. You wouldn't expect that because it's a very long period phase. It's 200 to 1,000 seconds. So that with those kind of long periods, you don't expect to get a lot of spatial resolution when you do these inversions. But the fits are so good. You can see these are the W phase. These are very long period. I don't have a time scale on there, but this is hundreds to 1,000 seconds in duration, these signals. And the fits can be so good that you can actually get quite a lot of information out of them. And we do get pretty good match. This is a body and surface wave model that was done by Ley et al., one of the best models available for this Maule earthquake. This was the 2010 Maule earthquake off Chile, and this is the model they got. And this is what we got using the W phase. So it's actually pretty similar. And this is significant because we're using a lot less data and a lot less sophistication in this inversion. The W phase, although it takes a little bit of processing, it's actually very straightforward compared to the surface and body waves that went into this inversion. The W phase is a lot easier to process and model, and so you can do it much more quickly, much more simply. And it looks like it gives you very similar information to what you get from more sophisticated inversions. So we then, bearing that in mind, we wanted to also look at different ways to do the inversions for this. And the way you estimate these fault slip models is you basically take your fault, and this shows the subduction zone. You can see the fault is along here, and you sort of split it up, you grid it up, and you calculate the seismic excitation due to each particular fault, or tsunami excitation due to each particular sort of subfaults, we call them, along here. And you add those up, and then you model your wave, and you basically invert that. And the problem with that is that may not be a very good way to represent the source. You're sort of, how should I say, you are sort of imposing a parameterization on your model that may not be very good. So, for example, the model might have very concentrated slip in a particular portion of the fault plane, and that may not be well represented by your grid, for example. I'll get into that in a little. So we wanted to try to come up with a more general way to do the inversions that would free us from this kind of parameterization. And we couldn't completely do that because we ended up having to use an underlying grid on our fault plane. What we do is we use a very much finer grid than other people use, but we still use an underlying grid. But what we can do is we can group that grid into arbitrary groupings, spatial groupings along the fault plane. So this is what's called a Voronoi cell. You see this line here. So anything inside whose center is inside that particular Voronoi cell will be given a certain amount of slip as well as rupture velocity. Similarly with this cell here and this cell here. So, although we still have to use an underlying grid for our fault, we can sort of group them in arbitrary ways. And by doing that, we can make that grouping part of the inversion, which I won't just show this equation to show that there's a lot of math involved. But basically what we now do is make the grouping of those little grid points part of the inversion, which is quite I think, a revolutionary thing to do. Inversions typically, if you were inverting for a velocity model, for example, with tomography, you might say I've got 5 layers and invert for the velocity values in those layers. You might even invert for the layer thicknesses, allow those to vary. But this would actually allow the number of layers to vary. So it can really look at it's called model selection. You can look at your selection of models and make that part of the inversion. So you're actually estimating which kind of model fits best along with which parameters in those models fits best. And I won't go into the mathematical detail. I will point out that this was originally devised originally adapted to geophysics by Toma Bodin, who's now at Berkeley. And that work is now being taken farther by Jan Detmar at RCS, and they both have worked extensively with Malcolm Sandbridge, who's developed it. It's called the transdimensional Bayesian modeling. I won't go into this. It uses Markov chain Monte Carlo sampling to sample the Bayesian posterior probability distribution. So if you know what that means, that's great. If you don't, we'll just skip and go to this slide, which shows why it's important. And this gets back to the parameterization. Now this is a very simple example, but you'll have to bear with me while I explain it. So here we've used, this is our model. This is essentially our initial model. This is our fault plane. We've decided, okay, we're going to have slip in the square area here. And this is our new inversion. So let me start down here. Here we've decided, let's use a fixed grid. This is how everyone else does these inversions. And we've decided to allow each of these grid points to be part of the inversion. We've used smoothing parameters on this model, and we've done an inversion, and this is the result we get. And you can see that it doesn't look anything like the initial model. And not only that, but if we estimate the confidence intervals on that model, which we can now do because it's a Bayesian inversion, we find that it's quite uncertain. The estimates of the parameters where we assign a parameter to each grid point is quite uncertain. So this is the best fitting model, essentially, this blue line here, and the parameter intervals are these dashed lines. And so you get pretty high uncertainties. You get a model that doesn't match the initial one at all. And now what we do is we say, okay, we're going to use these Voronoi cells now to group these grids so that all the cells that are part of this Voronoi cell here have a single slip. All the cells that are part of this Voronoi cell have a single slip, etc. So we can now group them arbitrarily and allow that grouping to be determined as part of the data fit. So the grouping of the cells adapts to the fit of the data. And if now all we do is we allow that grouping to vary as much as we want, to adapt to the data, but all we do is say we want at least 20 cells. So we're going to allow a lot of freedom in our grouping of the data, but we're going to insist that there are 20 cells. And we get a much better model than we got before, where we insisted that each cell had its own value, but it's still not that good a representation of the source, and the uncertainty intervals are still pretty high. And now what we've done here is we've used our new Bayesian technique, which allows both the number of the Voronoi cells as well as the grouping to adapt to the data. And this is the best fitting model, and so you can see this is one example of one of the best fit. Well, actually, this is the best fitting model. There are other models that will fit the data almost equally well, and you can see that here this Voronoi cell basically encompasses all of these grid points that went into our initial model, and then the others are outside that, and you can see you get almost a perfect fit and very low confidence intervals, very narrow confidence intervals. So the point of this is to show you that just by imposing a particular parameterization on your model, you can get very poor results in the inversion. And if you allow that parameterization to adapt to your data fit, you can get much better results. Not only that, but with the Bayesian approach, we can get confidence intervals on those, which is difficult to do. If you were doing this in a least squares inversion, that would be difficult to do here. I think I'm just going to skip this in the interest of time and point out that that, so this is, and just go straight to the results. For the Mali, this was the Chilean earthquake. This is our result. And you can see here, this is a result by GPS. I think this was published in Nature for the Mali earthquake. This is South America here, Pacific plate subducting. And so we got this slip offshore, which generated a large tsunami. And this was their result here. You can see there's a very high slip in the north here, very similar to what was obtained for the seismic model, quite high slip in the north. There's also this little patch in the south, which this model suggests is pretty big, pretty high slip in the south as well. That's the epicenter there. So you got sort of centers of slip that were north and south of the epicenter. This north one agrees pretty well between the geodetic and the seismic model. The one to the south is pretty strong in the geodetic, but not so strong in the seismic model. So again, you know, how significant are these differences? We really don't know. If we look at what we got indeed, we got very high slip in the north. That's about 35 meters, which is higher than the other models. This is getting 20 meter slip as a maximum. This got a similar 20 meter slip at the maximum. We're getting about a 30 meter maximum slip in the north, and it's so in pretty good agreement with these, except higher. And we get this very, very high slip actually in the south. But what we find is that that slip in the south is very uncertain. So now we can say that this slip in the north is quite, these are the confidence intervals. So you can see where it's blue, very low confidence interval, very narrow confidence interval, very well-determined result. So this is a very well-determined result, and this one isn't. Although we get very high results, very high slip down here, it's very poorly determined. You can see there's red, very wide confidence intervals. So we can now start saying, you know, which parts of the fault have low confidence and which have high confidence, and that's something that I think is very important. Also, the fact that the slip is higher is also consistent with the fact that in these other models, like this one, you have to use regularization. We don't have to use any regularization in this Bayesian approach. And that's probably why we think that's why we're getting higher slip here. It's essentially been smoothed out, and there's no way you can know whether that result is smoothed or not using the least squares approach. Whereas in the Bayesian approach, we don't have to smooth it all. You get full probability distributions for parameters such as rupture velocity, which is something you don't get in any of the other types of inversions. I guess I won't go into this too much, but basically we get much more information, not only about the best fitting models, but about how certain those are. And that's something that I think we really haven't seen in all of these finite fault inversions, almost all of the finite fault inversions in the past. So I think it's a really important result. I'm going to sort of shift gears now and get away from the inversion, the complicated inversions, and talk a little bit more about making better use of the new tsunami data that's available. Since 2004, there have been a lot of efforts at doing better, developing better observation platforms for tsunamis. One of the most impressive is the global deployment of what are called dart buoys. These are these ocean floor bottom pressure measurements, so they do very precise measurements of the pressure at the bottom of the ocean, and they can detect tsunamis with only a few centimeters amplitude propagating in the open ocean. And we now have pretty good coverage along the Pacific Rim for these dart buoys, so it's quite an impressive achievement, really. And in Japan, of course, and a few other places, they've also got a few cabled buoys, so these are essentially the same kind of thing, but they're run by a cable, whereas these have a buoy that transmits to a satellite and are somewhat more difficult to do the data telemetry. The cabled ones have much more reliable telemetry and are very nice. These are very expensive systems, and we really should be trying to make as much use of this data as we can, and that's what I'm going to be talking about in the remainder of the talk. I will talk a little bit about this. I'll try and realize this is a complicated slide, because what we've discussed is inverting for fault slip, trying to estimate the slip on the fault. And one thing we wanted to do is try to get away from that. So I'll just discuss the conventional way to do these, to invert tsunami data, or use tsunami data to estimate earthquake sources, is to take slip on a fault, generate the sea floor, the sea surface displacement, take the slip on the fault, generate seafloor deformation, translate that to the sea surface, and then propagate your tsunami. And that's how you would normally model a tsunami that's been initiated by fault slip. But you don't have to do it that way. You could start instead with the sea surface deformation and simply invert the tsunami for the sea surface deformation. And that has some advantages. It's a bit simpler, and it avoids the assumption that the tsunami is generated by fault slip. So if there are other mechanisms, such as the landslides, such as subsidiary faults that weren't on the fault that weren't on the particular fault that you're using, you could potentially pick it up you could potentially detect that by inverting instead for the sea surface displacement. And that's what I'm going to be talking about in the rest of the talk. So somewhat different from inverting for the fault slip. We're now going to be looking at the sea surface displacement. Is there anything else? I guess that covers it. And we're going to be using this was done by my student Jakir Hossan. I think I've got a picture of him somewhere. There he is. And we decided to apply this technique that's been used widely in other fields, in seismology, hydrodynamics, but also in medicine. It's been used to detect tumors, and even it's been experimented with in destruction of things like kidney stones in the body. And what it's based on is time reverse imaging. And so, if someone here, you show this guy yelling this hello, and this sound signal bounces off various places, and what we want to do is see whether we can use this signal that would be recorded in some place like, say, this wall here, and reverse propagate that. What would happen if we reverse that signal and pushed it back into the medium? And the remarkable thing is what happens is it's going to refocus right back into this guy's mouth and give him a shove. He'll be quite surprised because, it will focus right back into the point where it started. And that's illustrated here, where here it's a bit more of a elaborate thing. So here we have a source that gives off a signal. Those signals propagate through possibly quite a complicated medium, and they're recorded at these sensors here. Then we take these sensors, we reverse the signal, propagate it back, and what we'll find is that they'll reproduce that initial signal. And this has been demonstrated, can be demonstrated theoretically. It's been used in acoustics, very widely in acoustics. It's been used in seismology to reconstruct earthquake sources. It's never been used to reconstruct tsunami sources, and that's what my student Jakir Hossan wanted to try to do. Let's see, I'll just skip this one. I think I'll just skip, it pretty much says what the last slide says. I did want to do this. Do I have time for this? It doesn't work in the PowerPoint, but I wanted to illustrate this. Let me see if I can do this. It is here because it shows, this is an animation that was done by NOAA, and what it shows, it's a simulation. This was a Samoa earthquake, and you can see the tsunami propagating away from the earthquake. You can see how well it matches these dark buoys. There were only a few of them in place for this particular earthquake. But you can see that in addition to the initial wave, there's all these reflections that start bouncing around the ocean basin. And this signal will continue at any of these buoys. It actually continues for many hours after the initial tsunami. And what we'd like to do eventually is to take advantage of all that information. You can see reflections off the coasts. There are also reflections off all of the complicated seafloor bathymetry in the Pacific Ocean. And we'd like to eventually, we're not doing it yet, but we'd like to eventually take advantage of all that information to image the source of the tsunami. And so this time reverse imaging might allow us to do that. I will skip this since we don't want to talk about the math, I think. It talks about the equations. It just establishes that indeed the equations should be time reversible, which, they have to have certain properties. And instead, I'll just skip directly to this tank experiment. This verifies experimentally that shallow water waves that we use to model tsunamis with are, in fact, time reversible. So this was a tank experiment in which they had a little wave maker there, and they had sensors around it. And what they did was then reverse the whole apparatus and use the wave makers here with a signal that was fed into them that was reversed in time in exactly what they recorded before. And what you see is that you get this sort of, all this noise prior to the signal, and then boom, you get your source showing up. So they're able to image the source pretty effectively by using this time reverse imaging. And Jakir has done a number of many numerical experiments using this technique. So here's this is a numerical experiment. It's not a real case, and this was his source. He just put an earthquake well off northeast Japan in the Pacific Ocean, but did fairly realistic modeling using the actual bathymetry and recorded this signal at all of these. Imagine that he had a lot of dark buoys here, recorded that signal, reverse propagated it to see what he got, and he could re-image the source quite effectively. So you can see this was the original source, and if he did this whole time reverse imaging, he could re-image that pretty effectively. This required, though, a lot of observations. So the question is, well, really, we don't have that many observations. We don't have them surrounding the source. Typically, you've only got them on one side of the source. So practically, what kind of results could you achieve? Oh, this was also an animation, I think. Yeah. Let's see. Let's see if it works. Does it work? No, it doesn't work. Okay, can't get that one. Don't have that one. Anyway, so we wanted to see how this would work in the real world. And so, as I mentioned, the Northeast Japan earthquake was recorded by many, many sensors. We had a huge array of not only these dark buoys in the deep ocean, but also these regional sort of sensors as well as coastal tide gauges that are run in Japan. So it was really an unprecedented data set. The quality and quantity of data for this tsunami was far more than we've ever had for any tsunami in the past. So our question was, could we use this data in this more sophisticated way? Or actually, it's a less sophisticated way. So can we get by now with less sophistication because we have a lot of data that's very high quality? So yeah, I'll just quickly run through these. There are GPS buoys. That's another thing I didn't mention yet. They've got these buoys that float on the surface of the ocean or are precisely positioned with respect to a GPS network on land. That's these things. There were the dark buoys. I already talked about those, ocean bottom pressure gauges. There were also some cabled ocean bottom pressures. So these all recorded the tsunami with considerable fidelity. You can see this is the 10-meter scale here. So these are very large tsunamis. That's 10 meters there. This is that's 1 meter there. So the deep ocean, in the deep ocean, tsunami has much less height, but it did get up to a couple of meters at this deep ocean buoy, which is pretty remarkable. Near land, these are those ones near Northeast Japan. It got up to several meters, even out on the continental shelf. And then there were also some coastal wave gauges, which recorded obviously very high tsunamis. So a huge amount of data, and he has been. He worked on this for quite a while and has recently got some refined results. This I didn't show in the talk at RCS because they're more recent results. And what you can see here is his source model. This looks very similar to the previous ones I showed you for fault slip. This is actually sea surface displacement now. So it looks similar to the fault slip, but it's actually the displacement of the sea surface. And this is what we get using, he did some very careful work to do the conventional type of finite fault inversion, using the least squares approach, but some very detailed work. I won't get into that. This is the model he gets, so it's very interesting. It's also interesting that you can see this tsunami model has quite a pronounced tongue to the north here, and that is something that we don't see in most of the seismic and geodetic models, and may well be due to a landslide source. That's what Dave Tappan, and some other people have speculated on. So that's an interesting avenue that we're pursuing, and it looks very interesting. This is what he gets with his refocus source using the reverse imaging, and it's really quite similar. I mean, there's a lot more detail in this. You can see the peak here is much more narrow. You have this narrow tongue, as I said, to the north, and those don't show up as well in the refocused image. But this is really, he did a lot of careful modeling using the careful modeling and inversion to get this source to make it match the data really well. Here, you just refocus. It's just, there's no sophisticated inversion or anything. It's just it's like a refocusing of the time reversed images, and so there's no subjective choices about tuning parameters or anything. You just get what you get, and it's actually very close to in terms of maximum amplitude, the position of the peak, it's very close to the much more carefully derived model, and you can also see that it matches the waveforms really well. These are the ones that were actually used in the refocusing. And in the case this MTW, the green one, was actually used to actually match the data. The data is in red. The data are in blue. The green is the inversion. It was a least squares inversion, and that was done to optimize the fit to the data. And then the red is the TRI, and that was not optimized to fit to the data. It was just time reversed and refocused, and then we used that refocused source to predict the waveforms again. So it wasn't actually an optimized fit to the data, and yet it does a remarkable job, I think. It's almost as good in some cases as the much more careful inversion. In other cases, it doesn't do quite as well, but it's pretty good. It's really, really impressive. And the other thing about it is that it's very quick. There's no inversion, no tuning parameters. You just reverse the waves, repropagate them, and it's very quick. And so we think that this does have potential to be used in forecasting for tsunamis, both in regional distances. These are the waveform fits for regional stations that were not used in the inversion, like these two and these here. Sorry, yeah, these two and these here were not used in the inversion, and it gives quite a good fit to them. And then these much farther stations, they actually had to be adjusted. I'll talk about that in a minute. But they give remarkably good fits to the waveforms. And I want to point out that that the detailed waveforms are important. You know, you might argue that it doesn't really matter as long as you know the amplitude of the tsunami. It doesn't really matter, but it does for things like harbor impacts, where you can excite harbor resonances and you can excite very strong currents in harbors. Sometimes the details of the waveform will matter for that. So it is important that we can forecast what these detailed waveforms are, and we think we can do that now almost in real time using this kind of technique. I'm going to run through this really quickly because I think I'm running out of time. The other thing that we're working on, the other problem, well, when we got all this data from these recent earthquakes, 2011 Japan and 2010 Chile earthquake, we realized that there was a problem. And that is that from the far field, the observations don't actually match the modeling. So this is, the black one is the observation here, and if you use a particular source, you find that the modeled tsunami actually arrives quite a bit earlier in the far field. This is for a tsunami that's gone all the way across the Pacific Basin. It can arrive roughly 20 minutes earlier. The predicted waveform can be roughly 20 minutes before the observed waveform, has a higher amplitude, and the shape is a bit different. You see this funny sort of downwarp in the observation. You don't see that at all in the modeled waveforms. And that was seen before in previous tsunamis, but it wasn't until these earthquakes where we got a lot of data. You know, we always thought there was some problem with the bathymetry or something that we didn't quite get right in this observation or that observation. It wasn't until we got these big earthquakes that were well observed that we realized this was a systematic problem. We saw this everywhere in the far field for these earthquakes, and it was clearly there was some problem we had in modeling these. I won't discuss that. And it turns out that it actually is due to the fact that the tsunami is loading the Earth. So, you know, the standard way of modeling a tsunami is to have a shallow water wave that propagates over a rigid substrate. The seafloor is rigid. But of course the seafloor isn't rigid. The tsunami, if there's a wave, if there's a mass of water above the seafloor, an additional mass of water, it's going to load and elastically load the seafloor, and the seafloor will warp downwards because of that. And so if this is your tsunami propagating this way, you can see this sort of positive going water mass that's been added to the static situation. That's going to cause downwarping of the seafloor. And that's very small, you know, it's millimeters typically. But it's enough that it actually affects the tsunami propagation. And so Sebastian Alguer, my postdoc up there, he's been working on modeling that, and I won't go into how he does that. But basically, there are two effects. There's the loading as well as density stratification, simply due to the compressibility of the water in the deep ocean. And if you include both of those effects, you do a pretty good job now of modeling this. This is the data in black. The dashed line here in red is the standard way for modeling the tsunami, where you have constant density water, and it doesn't load the seafloor. And then if you start to include some of these effects, either the loading or the density stratification, you delay things a bit, and you start to develop this negative sort of excursion here. And then if you add them both together, you get pretty close to actually matching the observed waveforms. Using both of those together, density stratification and loading of the seafloor, you get this blue dashed line, and that's much closer to the observations. And I wanted to point out that this negative excursion here, that's due to the tsunami loading. So the tsunami mass is pushing the seafloor down, and that's causing this, the wavelength of that is quite broad because it's an elastic medium, so it's quite a broad wavelength. So that's ahead of the tsunami, essentially, ahead of the water mass, the seafloor is being depressed, and that's why you get this negative sort of excursion. We can now produce that in our modeling. And that is, well, I won't go into this in detail, but you can see that this was for the 2011 earthquake, and you can see the black is the data, the red and the blue are the different ways of modeling it, and you can see we've always done a reasonable job, at least in terms of the timing of the tsunami, for the tsunamis near the earthquake. There's no negative excursion, and the phase, at least, of the tsunami is about right. But as you get over here, you can see that you can do a very poor job. Unless you use the seafloor loading and density stratification, you don't produce this little negative excursion, and you can be, as I said, 20 meters out, 20 minutes out in your arrival time for your tsunami. So that's not really important for things like tsunami warning. You don't really care if the tsunami arrives 20 minutes later than you thought. It's not really going to affect anyone's evacuation. Same thing was true for the 2010 Mali earthquake. But it is important if you want to study the earthquake source. And so this illustrates what happens if you try to use uncorrected modeling to try to invert, much as I talked about earlier, for the slip on the fault. You get this kind of model. This is, again, South America, and we've inverted for slip. And you can see that you get the slip is well down dip. It's all been pushed to the east because the model waveforms are too fast. So they've tended to push the slip away from the observations. And all the slip is occurring down dip. It's not until you include these effects that you get the slip occurring up dip, and this is actually much more compatible with seismic models. I'm not going to show those now. I'm running out of time. But this model is much more compatible with the seismic models. You can see slip is occurring up dip where we know it did in fact happen due to we've got GPS measurements, etc., that show that. So this is much more compatible. So these effects, if we want to use these far-field waveforms to do detailed modeling of the source, we really have to include these effects if we want to get the right source. So that concludes. Yeah, that's the end of my talk. I'll try to summarize these so you don't have to read them all. So we've got this new probabilistic Bayesian approach to finite fault inversion, which makes this, making the data parameterization adapt to the data turns out to be very important in getting good models and getting correct assessments of the uncertainties in those models. If you don't use the right parameterization, it can affect both the model you get as well as its uncertainty. And we can address both of those with this new probabilistic Bayesian approach to finite fault inversion. It is very time consuming. You've got to let these models run for a very long time, but it does give you a fully probabilistic solution whose model parameterization has adapted to the data. I won't go into the rest of it. So I think that is but I do think that is a fundamental advancement in our ability to use both tsunami, geodetic, and seismic data to understand the earthquake source. We can now start talking about what differences in these source models are significant, and we can now say if we get 50 meters, we have valid error bars that we can add to that, and that helps us understand the physics of the earthquake source. The tsunami reverse imaging is quite an interesting thing. We think it could have practical application in forecasting, and particularly for far-field tsunamis. You don't have to do, the forecasting systems used now are either scenario-based, which is what the Australian system used, or there are NOAA is using a real-time calculation now to do forecasting, but they're all based on either scenarios or some kind of fit to the data. And we think this time reverse imaging is a much more robust way of matching your data and being able to forecast the tsunamis in the far field, if not even regional tsunamis. What we want to do is try to push this into using both the longer, 12 or even 24 hours of the tsunami propagation time, because you saw in that video how you get waves bouncing back and forth for 12, 24 hours easily, and that's all information that we should be able to use to understand the tsunami source. So we're not doing that yet, but I think that we will be able to use that in future to better image the tsunami source. But we will need to use this surface loading, because it turns out if you want to predict tsunamis that are propagated that far and that long, you have to include surface loading and density stratification of the ocean. I think that's it. Yeah, that's it. Thank you very much.